Those images are usually rendered in efficient formats such as PNG, GIF or JPEG that rarely reach 100 kilobytes in size. As discussed due to greater variation in colors and patterns, the popular areas, stored as compressed image files, use a larger proportion of disk space than the relatively empty non-cached tiles. Because of the dependency between the file size and the popularity of tiles, tile size can be a very valuable input of the neural network to correctly classify the cacheability of requests. During the training process, a training record corresponding to the request of a particular tile is associated with a Boolean target, 0 or 1, which indicates whether the same tile is requested again or not in window, as shown in equation. Once trained, the neural network output will be a real value in the range that must be interpreted as the probability of receiving a successive request of the same tile within the time window. A request is classified as cacheable if the output of the neural network is above 0.5. Otherwise, it is classified as non-cacheable. The neural network is trained through supervised learning using the data sets from the extracted trace files. The trace data is subdivided into training, validation, and test sets, with a 70%, 15% and 15% of the total requests, respectively. The first one is used for training the neural network. The second one is used to validate that the network is generalizing correctly and to identify overfitting. The final one is used as a completely independent test of network generalization. Each training record consists of an input vector of recency, frequency and size values, and the known target. The weights are adjusted using the backpropagation algorithm, which employs the gradient descent to attempt to minimize the squared error between the network output values and the target values for these outputs. The network is trained in batch mode, in which weights and biases are only updated after all the inputs and targets are presented. The pocket algorithm, which saves the best weights found in the validation set, is used. Neural network performance is measured by the correct classification ratio, CCR, which computes the percentage of correctly classified requests versus the total number of processed requests. Correct classification ratios, %, during training, validation and testing for Cartography and e-database. Shows the CCRs obtained during training, validation and test phases for Cartography and e-database services. As can be seen, the neural network is able to correctly classify the cacheability of requests, with CCR values over the testing data set ranging between 72% and 97%, as shown in table. The network is stabilized to an acceptable CCR within 100 to 500 epochs. Correct classification ratios achieved with a neural network for Cartography and e-database.